Okay, let's start. So good morning, everyone, and welcome to this Imagine Optic webinar, PSF optimization in 3D single molecule localization microscopy, or in other words, super resolution imaging using adaptive optics. I'm Vincent Renaud. I'm sales application specialist at Axiom Optics, and here is also Odorius Jasaitis, sales application specialist at Imagine Optic. So let's see. Okay. So here is today's outline. I'll start with a brief presentation about adaptive optics for microscopies. First, we will discuss what are optical aberrations and how do they appear in microscopy. Then we will review the fundamentals about adaptive optics, and then we will discuss how we can apply that for single molecule localization microscopy. Then I will give the hand to Odorius, who is going to give you an introduction about MicAO 3D SR, our adaptive optic systems for single molecule localization microscopy. And we'll give you a tour of how you can optimize your PSF and do PSF shaping for 3D localization. Then at the end, we'll have some time for question and answers. So this actually gives me the opportunity to let you know that there is a question window. So if you have any questions, please feel free to write them down here. We will have time, hopefully, for a Q&A session at the end. And in any case, we will try to answer most of the questions during the webinar. So I'm going to start with a very brief introduction of Axiom Optics. Axiom Optics is a US distributor, a North America distributor actually of Imagine Optic. We are specializing in optical instrumentations. We have a microscopy business unit. We are 3 in this unit, 2 on the East Coast and myself on the West Coast. We specialize in light microscope add-ons. For instance, we offer the rescan confocal microscope, which is an add-on that transforms a wide field into an enhanced laser scanning confocal unit. We also have a film system, camera-based film system from Lambert's Instrument. We also offer optical tweezers from Impedex, and of course the MicAO add-on for SMLM that we will discuss today. Besides microscopy systems, we also offer cameras. We have a wide range of cameras from regular CMOS to more advanced SCMOS from Amatsu. And for applications requiring even more speed and sensitivity, we offer the intensified CMOS from Lambert's Instrument. We also offer quality control solutions from Argolite. Let's now talk a bit about Imagine Optic. Imagine Optic is a company that started a bit more than 20 years ago by developing wavefront sensors. So they have a very big expertise in optical metrology. And then a couple of years later, they tackled the field of adaptive optics and developed systems for different applications, including high power lasers, bioimaging, and even X-ray and extreme UV applications. They offer components, so Shack-Hartmann wavefront sensor and also deformable mirrors, different technologies of deformable mirrors, as well as complete systems, especially for microscopy. Okay, so I think the first thing to discuss is, and it's probably something that you have all encountered, when you image something in microscopy, the quality of your image is going to be affected by some factors, including absorption, scattering, optical aberrations, and this also becomes more predominant as you go deeper in the sample. So probably you've seen it when you look at something at the surface of the cover slip. The quality of the image is pretty good, and as you go deep, the quality of the image starts to degrade. And that's again, that's because of absorption and scattering, which are things that we cannot correct. There are other ways to minimize it, but it's also and mainly due to optical aberrations. And this is something that adaptive optics will aim to correct, and basically to restore a perfect PSF, even if you go deeper in the sample. This gives me the opportunity to mention that adaptive optics can be implemented in many different ways in microscopy, depending on the setup. It's I would say used a lot in multiphoton microscopy, in light sheet microscopy, in InSTED, for instance, and also, of course, in single molecule localization microscopy. And every implementation will really depend on the architecture of the system. Here, in a couple of slides, we will focus on single molecule localization microscopy. If we're talking about optical aberrations, I have to give some reminders about wavefront and PSF. So PSF stands for point spread function. The wavefront is basically the perpendicular of the light beam. So what we see here on the left, for instance, for a collimated beam, all rays are parallel. So the perpendicular of that will be a straight line, and we call that a flat wavefront. This is an ideal case, obviously. In the case of a diverging beam or a converging beam, a perfect diverging or perfect converging beam, we will have a perfect spherical wavefront with no aberrations. But in reality, because when you go inside a sample, you encounter areas where the optical index is not exactly the same, it's not homogeneous, so the light will be distorted, and this creates an aberrated wavefront. Now, because we're talking about wavefronts, I have to mention Wernicke polynomials. Wernicke polynomials are basically a mathematical way to describe the wavefront, to describe the aberrations. It sounds a bit abstract like that, but if I mention words like astigmatism or coma or spherical aberrations, I'm sure those words ring a bell. And actually, those aberrations are Wernicke polynomials. And it's a very convenient way to describe aberrations and to describe the quality of a wavefront. So now let's review the key components that are used in adaptive optics. There are, I would say, two key components, two hardwares at least, the detector, the component that will measure the aberrations, and the component that will correct it. And then, of course, we need a piece of software to make them both talk together. Regarding the detector, this is called the wavefront sensor, and we're using a Schack-Hartmann wavefront sensor. It's a very, very broadly used piece of hardware. It basically consists of a CCD camera with a microlens array on top of it. And as you can see here, in the case of a perfect wavefront, each microlens will focus the local wavefront onto the CCD camera. But in the case of an aberrated wavefront, because locally the wavefront will be slightly tilted, then each microlens will focus the local beam with a slightly tilted, slightly tilted on the CCD camera. And by measuring how tilted it is, by measuring the displacement of the focus point in X and Y, we can reconstruct the wavefront. This is for the detector. And then once you've measured aberrations, you want to correct them. So there are several kinds of phase modulator that can be used. They actually all have their advantages and their drawbacks. And fun fact, they are all used in microscopy for different applications. But when it comes to aberration correction, it's very commonly accepted to use continuous membrane deformable mirror. And this is what we use and what we integrate in our system. So we have an hardware to measure aberrations. We have another hardware to correct them. Now we need to make them talk together. And the most direct way to correct aberrations is using what we call a closed loop. So it requires those two pieces of hardware, and it also requires a guide star. A guide star being basically a point source that will emit light and transmit the information of the wavefront to the wavefront sensor. This is a very direct, very straightforward way to correct aberrations, or at least to understand how to correct aberrations. Basically, we measure the wavefront using the wavefront sensors. We send the command to the phase modulator, our deformable mirror, that will correct it. And then we measure the residual wavefront. If it's perfect, it's good. If it's not perfect, then we run one more loop, and etc. And this is a closed loop. The main drawbacks of this technique is that it requires a guide star, which can be, depending on how you implement it, whether very expensive money-wise or very expensive photon-wise, because at some point you will need to send light to your wavefront sensor and not to your camera. And I'm sure we all agree here that every photon counts in microscopy. So another way to implement it or to correct for aberrations is to use not the wavefront sensor anymore, but to use a camera and actually the image from the camera to fine-tune the image quality. And so the way it works is we will look at some merit function on our image. We could be looking at a real sample, we could be looking at diffraction limited beads, and then we will look at, for instance, the contrast of that sample or the maximum intensity. And by using some iterative algorithm, we will converge towards a shape of the mirror that will maximize our merit functions, whether it's contrast or signal to noise ratio or a maximum intensity or whatever. The main advantage of this technique is that it does not require any guide star. It still works in some scattering media. But the drawbacks is that because it's an iterative process, it requires multiple images. And because it requires multiple images, you're more likely to bleach your sample. So this is something to keep in mind. As always, there is no perfect solution. I imagine that this image-based iterative algorithm might sound a bit abstract, so let me give you an example of the algorithm we use in our system. It's called the 3N algorithm. The way it works is we will look at a single diffraction limited sample, for instance, a 200 nanometer fluorescent bead, and we will look at a single bead and measure the maximum intensity of this bead. And we get this point. And what we do after is, using the deformable mirror, we add a tiny bit of aberrations. Let's say we add astigmatism, and we'll look at the same PSF, same bead, and we measure the intensity. And we got this point. And as you can see here, adding aberrations basically didn't improve the PSF at all. So what we do is we add the same aberrations, also a tiny bit, but in the other directions. So basically we remove a bit of astigmatism, and we get this point. And hopefully there is a law that says that the intensity of a diffraction limited bead or sample follows a quadratic rule with the quantity of aberration you apply. So with 3 points, you can plot this curve and determine what is the best quantity of aberrations, in this case astigmatism, you need to apply to get the best PSF. And here it is. So as you can see, this was done for astigmatism here, but obviously we will do it for other aberrations depending on what we know we have in our sample. So typically astigmatism, coma, spherical aberration, trefoil, and so on. And because we need 3 images per aberration, it's called the 3N algorithm. Overall, it requires roughly 40 images to correct your PSF to get a really nice PSF. So this is why we said before that this costs some time. I mean, this takes some time, couple of seconds or probably a couple of minutes if you need to do it several times. And you also have the risk to slightly decrease the intensity of the signal because of photo bleaching. Okay, so I think this is all for adaptive optics. Let's now discuss how this can be applied in single molecule localization microscopy more precisely. And let's start with a very quick reminder of PAM, STORM, and PAINT fundamentals. So SMLM is a wide field technique. It uses a wide field excitation, and it uses the specificity of some fluorophores to randomly emit photons. And so the way it works is we're not forming an image with a single frame. We need actually thousands of frames, and on each frame we will capture some fluorophores that blinked, and that will be off on the next frame, for instance, and we will fit the single fluorophores using a model, whether it's a Gaussian model or an astigmatic model or other non-PSF. We will fit it to localize the center of this blink, of this localization, and this is how we localize it with a certain accuracy of localization. And with thousands of images, we sum up everything, and then at the end we can reconstruct our final image. But because it's wide field, we only get a 2D information, right? I mean, as long as we are in the depth of field of the objective, we will capture all the light from here, and they will all blink randomly, but we will have no information about Z. So what we do to get the information is we need to encode in the PSF, in the shape of the PSF, the Z information. And to do so, we tune the PSF, the most common way to do it is with astigmatism or with any PSF that will be different depending on where you are in Z. So for instance, astigmatism, if you are above the focal point, you will get an horizontal line. And as you move below the focal point, you will get a vertical line. So by fitting the extension of the PSF in X or in Y, you can get the Z information. And as you can see, I've talked a lot about PSF, and especially in single molecule localization microscopy, the quality of the PSF is very important because it will be driving the imaging performances of your system, and especially the number of counts, of localization counts, also the number of photons per count, and also the quality of your PSF shaping for quality and symmetry of your PSF shaping for 3D localization. So our system, our solution for that is the MicAO adaptive optics unit. It's an add-on for inverted wide field microscopes. It's compatible with whether 60x and 100x objective lenses, whether EM60 or CMOS cameras. It has a bypass options, etc. And it brings two main things. The first thing is it corrects aberrations. So this is all we discussed before. You will get basically a better SNR, so more light. It will be more focused, so not as spread out, whether laterally or axially. So this will also increase SNR. Because you will get more photons, it will also increase the localization accuracy, which is directly proportional to the number of photons you collect. So this is one thing. And the second thing is because we can actually correct aberrations, we can also apply aberrations. And for instance, we can apply astigmatism. I mean, we could think this is what a cylindrical lens do. Yes, correct. But with the main difference that first, this is a pure astigmatism because it's corrected from other aberrations. And then we can also, because it's an active component, we can also tune the quantity of astigmatism we apply if we want to get better axial localization accuracy or better lateral localization accuracy, for instance. And this is very easy to tune. So once you've got your PSF shaping, a very common thing to do is to acquire a calibration curve. So for astigmatism, the calibration curve is basically the extension of the PSF in X versus the extension in Y. By plotting the ratio, or actually the difference between those two extensions, you can reconstruct this calibration, this line that we have on the right, the calibration curve, that will give you the Z position, the actual position of your fluorophore compared to the focal plane. So what happens if you don't use adaptive optics? Well, this is what we have here on the left. This is with a cylindrical lens. Typically, when you're not using a cylindrical lens, the calibration curve or the extension, the astigmatism is not symmetrical, and so the extension in X and in Y are not symmetrical at all. And this is an issue because the consequence of that is many localization, many localization counts are rejected because of this issue. And it happens usually much more on one side of the PSF, mostly because of spherical aberrations. And this is what we can see here. If you look at the number of counts on the bottom right of this slide, we see that for the first half, there is not much difference, but as soon as you go on the other side of the focal point, then there is many more localization acquired with MicAO compared to with the cylindrical lens. Maybe a more visual way to see that is with this slide. So what we saw before, it was at the surface, so there was already improvement at the surface. But as you go deep, and here especially at 30 micron deep, it's even more obvious. There is so much spherical aberration that it totally destroys the symmetry of the astigmatism. And if you look at the cut of the PSF in XZ or YZ, you see that it looks pretty much the same. And this is an issue because we basically want it to look different because this is how we're gonna localize where it is in Z. If you correct it, you get what we have here on the right with a beautiful symmetrical austenitic PSF. And here you get a very linear calibration curve. It's very easy to plot and very easy to get the Z information. So adaptive optics basically restore the symmetry of the PSF and correct the calibration curve. Before switching to the next slide, again, I will emphasize on the fact that MicAO is using a deformable mirror, which is an active component. And because it's active, you can pretty much put the shape you want, not everything, but you can shape the PSF, you can tune the PSF as you want, and you can do that, and you can put more or less astigmatism, but you can also put a different shape, which is a tetrapod PSF. Because one issue with an astigmatic PSF is it basically spread out too much after plus or minus 500 nanometers. Depending on how much astigmatism you put, of course, but more or less plus minus 500 nanometers. And then you don't get enough signal to localize your PSF. This is for most of applications, 1 micron for single molecule localization microscopy is way enough, but sometimes it's not. And when it's not, you can do PSF shaping that will enable to image at the same time fluorophores over a bigger Z range, for instance, up to 3 or 4 micron with a tetrapod PSF. Tetrapod PSF got very famous with the Morner lab at Stanford because they use it a lot for single molecule localization microscopy. And it's something that can be created with the MicAO. And as you can see here, we have the XZ and the YZ cut of those PSF. And we see that the tetrapod PSF extend much further above and below the focal plane. So to finish, and before giving the hand to Audrius, I want to remind you maybe a couple of take-home messages that MicAO 3D-SR is an integrated adaptive optics solution for single molecule localization microscopy. You don't have to build your own system. It's using advanced wavefront control and PSF control. It has a high versatility. You can use it to perform 2D single molecule, 2D SMLM, but also 3D with astigmatism, 3D with tetrapod for imaging over a bigger range. It's very stable. So if you need to do experiments over a couple of hours or even a day or two, it will not change. And yes, it's an all-in-one solution. And finally, I want to acknowledge Leica for their help in these webinars, because as you will be able to see very soon, they're letting us use one of their microscopes. So that's all for my presentation. Let me now give the hand to Audrius. Audrius, can you take the hand? Audrius? We can't hear you, Audrius. We still can't hear you.
Okay, now it's okay now?
Now we can, yes, now we can hear you. Perfect. So I'm going to mute myself.
Does it work? Does it work?
Okay, that's fine.
Switch to the sound.
Okay, okay.
Still echoing. Switch over to the.
Okay, okay. Can I? Yeah.
Nobody speaking. Sorry, was it the later? Okay, let's try this.
No?
Matthias, I think you, Martial, sorry, you need to turn off your microphone. because we're hearing an echo.
Turn off your microphone. Okay. No.
We still have an echo. There is one microphone that is not muted.
No?
No, I think it's for me. Vincent, maybe it's for you.
Can you mute?
See. Well, I will try to anyway. So welcome everybody to the hands-on part of this webinar. And thank you, Vincent, for this very nice introduction. This really simplifies my presentation here. So basically, in this part, I will try to show you how MicAO 3DSR looks like, we will try to correct aberrations on the surface of the cover slip. We will look into 3D shaping of the PSF. And as well, we will try to go deeper into the sample and see how to correct aberrations deeper in the sample and how adaptive optics can help improving the PSF. So MicAO 3DSR here is linked, well, basically it's an adaptive optics device for correction of aberrations, specifically designed for easy implementation on the inverted frame microscope. Basically here you can see it's attached to the Leica microscope. So here goes a special thanks to Leica France, who kindly provided this microscope to us for this webinar. As Vincent described already, this device can do a couple of things to improve the imaging quality. But first, by correcting system aberrations, so-called, let's say, aberrations which are coming from objective or other optics inside the microscope, you can already improve the quality of your PSF, improve the number of counts in the focus. As well, we can correct sample-induced aberrations, biological sample-induced aberrations, which also significantly reduce the imaging quality. And this is where MicAO 3DSR really stands out in terms of improvement of the signal. The second thing, we can apply different types of beam shaping in order to break the axial symmetry of the point spread function in order to do 3D imaging and single molecule microscopy. So as Vincent showed you, we can use Astigmatism, we can use Tetrapod PSF, and this is what we will try to look very close. Actually, there is a third thing which MicAO can do. It can correct sample-induced aberrations from deep in the sample. So actually, this is probably the only method which allows you to go deeper than 10 micrometers and still do 3D imaging with high precision. So now we have examples of imaging at 30, 50, even 18 micrometer depth inside biological samples. So still a little bit, a couple of words about MicAO. So basically, it's as you can see, it can be easily attached to the emissions port of the microscope, and inside it contains a deformable mirror, which has 52 actuators, and this is sort of optimum number of actuators for correcting aberrations which can be found in the microscope. Device is functioning as an image relay, so we are attaching the image plane, and we have an image plane at the exit of MicAO, and inside there is a backfocal plane where the deformable mirror is installed. We do calibration of the device using Sharp and waveform sensor. So basically, we replace the camera using this device, which we call wavefront imager. So we simply detach camera, we attach wavefront sensor. We use like a single point source for measuring the wavefront. And this way we do calibration where we measure influence of every actuator on the wavefront. And after this, we do the first optimization, the closed loop measurement, which gives us already optimized, like correct all aberrations of the optical setup, like system aberrations. Then we replace the camera, and all other improvements of the point spread function, we are using image-based algorithms. So mostly we use 3N. In our software, this is what we use 3N, and we try to use fluorescent beads because those are non-bleaching samples, non-bleaching specimen, which is easy to work with, and you can also judge the quality of the PSF using fluorescent bead. So I guess we can turn now to the hands-on part. I will try to share my screen. Okay, can you see my screen?
Yes.
Okay. Right, so here you can see it's distorted, it's not all the screen. Yeah, okay. Basically, here for this demonstration, we are using Micromanager to acquire images, and here you already see. I have a sample of fluorescent beads embedded in agarose. So there are beads on the surface of the cover slip, and there are beads somewhere deeper. So this one is on the surface of the cover slip. And I will start with this we'll start by showing already optimized point spread function. So we would you could judge what are the differences of the point spread function. How the good point spread function should look like. So we have in the focus, the intensity is maximal. And if we go to one or the other side of the focus, the intensity is dropping pretty quickly. And basically, we are getting featureless shape of the point spread function. But intensity is very low because we see this here pretty well because it's auto stretching, but it's auto scaling on every frame. But if you go back, you see that in reality we have close to 30,000 counts. The same on the other side, you get almost featureless point spread function. So in order to correct aberrations, as I mentioned, we already said that we are using 3N algorithm. And to demonstrate this, I will actually load the shape. Basically, our software allows to save any shape of the deformable mirror we have. So currently it's using 3N shape, which is like optimized shape. I will load something which I made a bad PSF. Basically, I added aberrations to optimized PSF. So if we look or defocus this PSF, we see that we have rings. That will be spherical aberration, and the maximal intensity is going to the side. So that's probably comma. And I think I added a little bit of astigmatism, but maybe too little. Okay, this is comma, which is really very visible. So I will now try to optimize this point spread function. So I leave my system close to the focus. Basically, I'm trying to maximize this value. So it's over here. And then I go to our plugin window, choose optimization mode, and this changes our interface to Zernicke coefficients, where we can choose the modes which we would like to correct for. So, like a first approximation would be to choose the third order aberrations, like 2 astigmatisms, 2 commas, spherical aberration, and trefoils. And we will I will start acquisition, and you will see some changes. Basically, the algorithm goes through every of these modes and then tries to add and subtract a small amount, like 50 nanometers, that's the search limit, 50 nanometers of all of those aberrations. And we should follow this value here, which is the maximal intensity. We started from 17,000 counts and we gradually increase by correcting aberrations. So when we go through the cycle and when it's finished, we see that we, instead of 17, we've got 24,000 counts. So I do accept the optimization, and if we look at the PSF, it's already pretty nice. Okay, so there is a little bit of spherical. So this is basically algorithm is sequential, so that's why we probably need to repeat this for the spherical aberration selectively. So I'll choose only spherical aberration. One more time. And here the process is artificially slowed down. It can be faster. Basically, we have very long integration time, and maybe I should also include focus. Long integration time in order to see what is happening. This can be definitely faster. Okay, so that's the idea of the 3N algorithm. Okay, so I will try to optimize the. Well, the next thing is to show you how the 3D breaking the axial symmetry works. So we can start with the astigmatism. Basically, we have here, well, we chosen, will apply 100 nanometers of astigmatism using deformable mirror. And this is type of astigmatic PSF you can expect to have using deformable mirror. So basically, I'm extending to one and the other side of the focus. You can see that astigmatism extends very long and homogeneously to both sides, symmetrically to both sides. So I did, just to save the time, basically for making a calibration curve, we would have to take a Z stack. But to save the time, I already took this beforehand. And I will simply import it and see schematic stack. So it's basically the same what we see here. And I will just quickly run a thunderstorm procedure for calibration with some standard parameters. And you can see that the calibration curve is very symmetrical. It takes, you can use almost 1 micrometer at depth, probably a little bit less. We would also probably recommend to use a little bit less astigmatism because, well, deformable mirror allows to use less astigmatism, and you do get slightly larger Z range and then better localization precision, because the more astigmatism you apply, the more you distribute photons in Z, so your maximal intensity is smaller, and that way you probably lose the localization precision. Here I used 100 nanometers only for show you basically the quality of achievable function. Another thing which Vincent already mentioned is that we can use Tetrapod PSF. So this is what I already preloaded to the shape. Basically, Tetrapod PSF is a combination of different types of astigmatisms. And here you can see in the moving window here, this is how it appears. Basically, the point spread function splits into two dots, and then these dots are separating, still keeping quite, or staying visible for quite a long Z, let's say. So this allows a much larger Z range to be examined. Okay, so I will probably load again these two stacks because I also pre-recorded Tetrapod PSF. Okay. So we should have a similar, like this is Tetrapod here, and this is Astigmatism, and I will try to synchronize them. So you can see, if we look on the left side, Astigmatism, it's almost at the edge, but the Tetrapod is still quite usable. And if we continue going deeper, Astigmatism is not usable anymore, but Tetrapod is perfectly fine, probably until here. This is not auto scaling, so probably it's I don't know if you can see this, but it's still visible here. And the other side as well, you can see that Tetrapod PSF is much longer visible. Okay. So after the webinar, I think I will arrange a small presentation combining all the results, all the stacks which we acquire here, so you can examine these on your own, let's say, data treatment routine. The one more thing I would like to show you is how to optimize aberrations deeper. And now I'll just need to find the fluorescent bead, which is a little bit deeper. Maybe we have some questions already, which we could discuss.
Yes, can you hear me?
Yes.
Hello? Okay, perfect. Yeah. So we had a couple of questions. I already answered them privately, but it was actually posted public in the question tab. But if you missed it, let me reformulate them. So the first question was that because we only use a single, in this example, we use a single diffraction limited sample. So the question was, does that mean that the aberrations are going to be corrected only for that small area in the sample, in the image? And how would you get homogeneous correction for the whole field of view? And that's a very good question. So yes, that's correct. When we run the optimization, it's obviously optimized for this area in the field of view. Now the aberrations will be pretty much the same all over the field of view. And that's even more true in single molecule localization microscopy, where we typically use a smaller field of view than, for instance, in confocal or in wide field. But yes, it's correct. It's optimized for one field of view. Typically, we choose a sample which is in the center of the field of view, and so on the very edge, yes, you can basically find field distortion and other things like that. Another question was about very similar question. When we correct the PSF, we obviously do it in one plane. So how does this apply when you go in 3D? That's also an excellent question. And yes, that's correct. Actually, I would say it's even more true. The aberrations are much more depth dependent than they are regarding the field of view. Basically, you get a lot of spherical aberrations as you go deep. But that's true for, let's say, a couple of tenths of microns, not for 1 micron or even 3 to 4 micron. You could maybe start seeing it for 3 to 4 micron, but it would be very little. So practically speaking, in single molecule localization microscopy, this does not really matter. Now, if you want to extend that to other techniques like spinning disk microscopy, where you are more likely to do a Z-stack over 30 or 40 microns, or even, I don't know, even 100 microns, then yes, you will run the optimization in one plane. There are two options. Actually, you can run optimization in the first plane and run the same optimization in the last plane, pretty much what Odorus is doing right now. And then load those two shapes and say the mirror, we have those 2 points, plot a linear regression between those 2 points and adapt your shape depending on where you are at between those 2 points. Or the other strategy is to use a model of spherical aberrations, and it will basically correct for the spherical aberrations as you go deep in the sample, taking some assumptions. So it's not as accurate as a real correction. And yeah, I think the last question was from Vitotas was a bit more personal. So not personal, but like sharing his thoughts. So I'll not share it. You can. That's all for the questions. So you can go whenever you want, Odorus.
Yes, I'm almost. So I just have to restart my software. And okay, so here's the bead roughly at 20 micrometer depth. And the shape of the mirror, which I have, is a surface correction. So if I now go in and out of focus, you will see that it's quite just a white dot on one side of the focus, and on the other side we start to see the typical rings of the spherical aberration. So if I apply astigmatism now, you can see that it's distorted and not very usable. Like it splits into two dots very quickly, and almost doesn't extend on the other side of the focus. So I will now try to selectively correct for spherical aberration and maybe some other aberrations which might occur in order to try to basically restore astigmatic imaging. Spherical. So here again, we are looking at the maximum intensity in order to see progress. Okay, so this is, as I was mentioning, it's an iterative algorithm, so we should repeat this. The same. I think the comma as well. Don't see the bright dot on one side, you do not, and there are still some rings. Also, it's not there. So the process is iterative. Basically, you need to patiently follow these values. Maybe one more time. So we started something like 5,600, and now we're reaching 10,000 counts. So this is like a typical improvement from at 20 micrometer depth. We are almost doubling amount of photons. Okay, so at this point I need to correct a little bit comma. Now it's symmetrical and intensity is very low now. So this is the feature of corrected PSF. You see that intensity drops very quickly. So if I apply now astigmatism, you see that it's not distorted as much. Let's say we probably could do even better, but at least it's symmetrically split on both sides. So the point spread function becomes symmetrical. So I can well, let's save this shape just in case. So we'll call this 3L deep. Now we'll load again a 3N shape, which was the surface correction, just to remind you how the point spread function was distorted by astigmatism. So it's totally unusable. And this is only 20 micrometer depth. And deeper would be even more complicated. Okay. So I guess at this point, the hands-on session is probably over. We can probably discuss more questions if we have. Vincent?
Yes, so we did not get any. Oh, actually, sorry, my bad. We have one. No. Thank you for your answers. Okay, no, we do not have other questions for now, but we can maybe take a couple of minutes. If you have any questions, that's now. And of course, you can contact us later. We will reach out back to you anyway with those recordings and with the link for the recorded webinar. But yes, I think it was a very strong message. I mean, the correction at 20 micron, looking at the PSF before and after, it was really obvious that the quality of the PSF has been much improved.
Yes, and I will just repeat that I will I will try to share the data.
Yeah, can you maybe put back the new PSF at the surface? Sorry, not at the surface, at the corrected at 20 micron, so we can look at it.
Yes, sure.
Okay, I don't see any other questions, so I hope it was interesting and enlightening for all of you. And if you have any other questions, please let us know. And in any case, we will reach out back to you in probably early next week. Okay, I think we can close this webinar. Thanks so much all, and have a good day.